Hi everyone, I'm Celia, a research machine learning engineer at Zama. And to accompany the release of PPML 1.7, we've added a new use case called DNA testing using fully homomorphic encryption. In this demo, I will show you how the space works and explain what's happening behind the scenes. So why is DNA data so important? DNA testing can reveal incredible insights about your health, ancestry, genetic traits, and so on. However, DNA testing platforms analyze your data in plain text, making it vulnerable for hacks. And FHE is a great solution for this because it allows DNA analysis while preserving your privacy. In this space, we focus on the ancestry analysis use case, and our work is strongly based on the winning solutions from the season 6 of the Zama Tree program. So we start by simulating a genome using one allele for simplicity. By the way, the training data set is synthetic. We used pure blood founders from 5 distinct regions, crossed and mixed over n generations. And to create a new descendant, we randomly combine genetic segments from each ancestral allele. On the cryptography side, we generate 2 keys, a secret key for encryption and decryption, a public evaluation key to allow the server to compute on encrypted data. We encrypt the data thanks to the secret key and send it to the server along with the evaluation key to a computation server, which would be hosted by a DNA testing company. Once the server receives the data, it can process it without ever decrypting it. So now let's see how it works behind the hood. The allele comes from the 22nd chromosome, which is a crucial part for tracing human evolution and migration. So here, the model processes the SNPs at key positions on this chromosome. And in practice, the allele is represented as a binary vector of size around 1 million entries, where each value indicates the presence or the absence of a specific SNP. And to determine the ancestry proportion for each region, our approach works in 2 stages. In the first stage, which is called the based modules, the allele is divided into n windows. Each window is assigned to a classifier to estimate the ancestry probabilities based on the SNPs in that region. Each classifier is trained independently, but they all share the same hyperparameter configuration. So once we get the estimated probabilities across all the windows, we can refine them by correcting the error made in the first stage using a smoother module in the stage 2, which uses information from neighboring windows to produce more accurate predictions. So the goal here to have 2 stages is first get the primary estimations and then refine them for a higher accuracy. We start by splitting the initial training data set into 2 sets, one to train the based modules and the second one to train the smoother module. In this part, we split the allele into n windows. We also add additional SNPs on either side of the window to better capture the dependencies. We instantiate n logistic regressions. Keep in mind that FHE operates only over integers, so you have to quantize your models. And in concrete ML, you can do it easily using this hyperparameter. We train the based modules. We also compile them to generate the FHE circuit and the cryptographic parameters. Once the first stage is completed, we can predict the estimates probabilities on the second set using the based modules, of course. We rearrange and reshape the data. We instantiate the smoother module, quantize it, feed it, and compile it like we did in the first stage. And finally, we save our models using the FHE model dev API, which will generate for us the server and the client zip files for the deployment. So now that the computation is done in the server side, we can send it back to the client. And to retrieve the presumed ancestors of the last simulated descendant, we decrypt the data using the secret key. So this demo showcases a scenario involving highly sensitive DNA data where FHE can provide a solution to preserve user privacy while enabling cloud services to perform computations. So thanks for watching and stay tuned for new updates in ConcreteML.